I'm going to be going over an example of a 3-bus power flow analysis. I have the voltages given. If the voltages are not given in an example that you're looking for, you want to use iterative methods. I'm not going to be going over that because there's pretty good tutorials already that cover that. And the lines are given for impedances. We have a base power that's given as 100 MVA. We have a slack or source bus, and then 2 load buses. Some things to note are the arrows here represent real and imaginary power. Make sure your calculator is in degrees, and we're going to be using conjugates quite a bit. It's just turn your plus to a minus. And if you have a impedance in between your source and source bus, you want to change it to a current source. And to figure out the current source, you just use Ohm's law, V over impedance. And I think that's it to get started. First thing you want to do is turn the line impedances into admittances. And that's just 1 over the impedance. So 1 over, let's make it visible here, 1 divided by 0.02, which I have a parenthesis, plus 0.04 I, 10 minus 20J, that's what I got here. And then the next 2 are 10 minus 30I and 60 minus 32I. From there, you can make an admittance matrix. It is not required, but it helps later on in finding our bus currents. So to find Y11, we use this here. You just add up all of the admittances connected to that bus. And in our case, for Y11, we got a line going to bus 3 and one going to bus 2. So you just add them together. So in our case, it's 10 minus 20I. Straighten that up a little bit. Plus 10 minus 30I, and that's 20 minus 50I. That's what I got here. And then the rest you just copy from above, except if you note that it's a negative in front of all these. So make sure you put you swap your signs, negative 10 and plus 20. It's pretty easy to forget about switching a sign, so just double check yourself afterward. And then if you do the rest of the matrix here, this is how it will look. And using that, you can find your bus voltages, but we already know that. So what we're going to be using it for is to find our bus currents, our I1, I2, and I3, by taking that matrix and multiplying it by our 3 bus voltages. You may have noticed that I label these as A, B, and C. I'm going to label those into my calculator as such because it's just going to help on later in this example. And I already have them saved in here, but I'll redo. So for example, A is 1.05 stored as alpha A, and bus B is 0.98183. Whoops, gotta have a parenthesis in front. Second angle, negative 3.5035, stored as alpha B. And same thing for C. Okay. So to find out these currents, we want to go ahead and make the matrix, or put the matrices in our calculator. To do that, go to second, quit, up, data matrix. And I already have them made, and it's kind of lengthy to redo them all. Well, what I will do is I will make a matrix for the voltage, which is, well, we'll make it as V. Oops. V. And it's a 3 rows, 1 column. I already got a V in there, it's saying. So never mind, I won't make it. Or I'll just make it another variable. I just won't use it later on. Oops, let's have it as I, and we'll have it 3 by 1. And then we just put in our bus voltages, 1.05. I'm not sure if I'm allowed to do this or not, but putting in B. Oh, yeah. So you just put in your A, B, and C in there. And enter. Or sorry, just go back to home. Then you double check, make sure you put in everything right by typing in V. And boom, you got your voltages. And I already have you do the same thing for the admittance matrix. I already have it in here. So I'm just going to go Y times V. And let's go on to the next page. So that answer gave me 3.9 minus 1.8 J, negative 2.54 plus 1.2 J, or 1.28 J, and so on for bus 3. So I wrote them out here. And these are our bus currents, which is useful later on, and you'll see why. And there's also a second way to do it using this formula here. Let me get this. So our bus that we're looking at is going to be labeled as I. So let's say we're looking at bus 1. We look at Y11, and then it's V1 minus V1, so it's 0. So we cancel that out. That doesn't matter to us. Then we have Y12 times V1 minus V2 plus, and then we just have one more, Y13 V1 minus V3. You can see that I did that here. So on our calculator, we type in our admittance and then just A minus B and then A minus C here. And you also get the same answer that we got from the matrix. So that's a good way to double check yourself. And you can do the rest for these also to double check. And from there, we can find our bus powers. Power going in or power going out, which is SI, I being the bus we're looking at, equals VI times current, and it's the conjugate. So if we're looking at bus 1, it's going to be A, which is our voltage at bus 1, times then our current, which was 3.9, and then it's minus 1.8 J. Since it's the conjugate, that turns into a plus. And then you get your power in, this is in power units, so remember that. and our base unit was 100 MVA. So you just multiply these by 100. So our actual answer is S1 equals 409.5 plus 189J MVA. And let me just do this in the calculator just to make sure I'm not lying to you. So we can say A, which is our voltage, times, and I said 3.9 plus 1.8 I. And yep, there we go. They match. And then you just multiply each of those by 100. And you do that for the rest of the buses. Oh, I lost my video there. But I'm using the same technique for the rest of the buses. And we know that we're on the right track because if you look, if you remember, this was our source bus. And we got positive and positive. And we got negative, 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 negative. So this is supplying our power, and then this is consuming power. So that's how we know that we're on the right track. And now we can find our line power. And to do that, we use the formula here. I should have said Sij is equal to Vi times Ij, and then same thing for Sji equals Vj Iji, then it's the conjugate of the current, and that's just the current, not the voltages and current. I should maybe separate that a little bit. Because voltages stay the same. And an easy way to look at this also is by saying it's the voltage of the bus you're looking at times the admittance of that line, and then it's V voltage that we're looking at on the bus minus the bus we're going to. And I'll do an example here. So for example, S12 is equal to V1 times the admittance of Y12 times V1 minus V2, and it's the conjugate of this. So this is what we're going to have kind of typed in our calculator here. And I'll do that here. So we have A times, and for our conjugate, it's second math, complex is 5, conjugate 1, and then we have 10 minus 20j times a minus b, a minus b. Yep. And yep, our answer matches what we got. I have written down here. Just remember, multiply it by 100 to get your actual answer. So this is what the calculator gives you. And our S12 is equal to 199.5 plus 84 JMVA. Can I see how those relate? This is in power units. You do the same thing for S12, S13, 31, 23, and 32. And once you figure those out, then we can find our line losses, which S12 loss, I can say 1, 2, or 2, 1, doesn't matter now, is equal to S12 plus S21. You might be thinking to yourself, it should be, we got point A and point B. In your head you should be thinking it's A minus B, and you're correct, but it's kind of like a minus a negative, and it just becomes a plus. And that'll become visually, what's the right word? I don't know. You'll be able to visualize it later on, so you'll understand why this is the way it is. So we've got 1, 2 is 199.5 plus 84J plus 2, 1, 181. You can kind of see how that works out already. So it's going to be 199.5 plus 84 J, parentheses, plus negative 191 67 J. Oops. Equals 8.5 plus 17J, and this is an MVA because both that I used were the MVA units. And you do the same thing for S13 and S23 loss, which is equal to S13 plus S31. And to save some time, oops, I thought I had them wrote. Oh. Maybe not. So let's go through them together here. S13 is 210 plus 105J plus and 31 is negative 205 minus 90I 5 plus 15I MVA. And 23 is negative 65.6 minus 43.2 J plus, and 32 is 66.4 plus 44.8 J. .8 and 1.6. So this is our power being lost in the lines because of the line impedances. And now we have everything we need to graph it out back in our original picture here. Because we have our bus powers, our line powers, and our line losses. Here we go. So I got my blank picture. This was bus 1, bus 2, and bus 3. And that's just a matter of plugging everything in and double check to make sure it all looks right. I said our S1 was, our real is 409.5, 409.5, and our imaginary is 189J. And these are both an MVA. I'm going to have a lot of crunched up space, so I'm not going to label them all. S2, and this is a negative, and this is a negative. So see how the arrows are pointing to the bus? These are going to be pointing away from the bus. And same thing with S3, negative and negative, so they're going away. And these are all MVAs, remember that. And now our line powers. So we have S12 is this here. And keep in mind of the direction, it's positive and positive, so the arrows are going to it like this. So it's 199.5, and we have 84J. And we look at 2-1, it's negative and negative, so it's going to the bus now. And our real is 191. And imaginary is 67J. And then we can find out what our loss is. We can predict that if we look at our real, it's 199.5 and 191. So we would imagine that it's we lose 8.5 MVA, and we're looking at the imaginary, so we'll lose 17J. And lo and behold, 8.5 and 17J for S12 loss. And we label it like this, 8.5 and 17. And, or 17J, however your professor wants it. And then 2 to 3, we have negative and negative again. So it's going to the bus, And it's 65.6 and 45.2. And 3 to 2, it's positive and positive, so it's going away. And that makes sense. You can see how there's that flow. Sometimes it doesn't actually work out like that, but you can be pretty confident when it does look like this. And 66.4 and 44.8. And let's do 3 to 1. 3 to 1 is negative and negative, so it's going to the bus and to the bus. And it's 205 and 90. And 1 to 3, we'd expect power to be going this way. But let's check ourselves here. And it is 210 and 105. They're both positive. So yep, they are going away. That was 210 and 105. And we'd expect our loss to be 5 and 15? And it is 5 and 15. 5, 15. I will put a J there. And 2 to 3 is 0.8 and 1.6. 6. J. And that is it. And you can just double check yourself, because power in is equal to power going out. So make sure that we got 210 coming out and 199.5 coming out. 210 plus 199.5 is equal to 409.5, and same with the imaginary. 105 plus 84, 189, and it is 189. So you can do all that to check yourself, and that is it. Thank you for watching.